So this lesson will be the last lesson of Unit 2. This is going to be building quadratic models from verbal descriptions and data. And this is going to be from section 4.4. So this lesson will mainly focus on the ability of using the TID4 again to input data. And again, we're going to utilize a couple of tools. One's called the quad regression, and the other one's the linear regression, which we did the linear regression last time. So we're going to focus on the quad regression tools to write quadratic equations, or the linear regression to help us build a linear equation that supports a scatter plot that's being used in the data. So as I said, we had some data that was linear, and then we have some data that's not linear, but they also could be classified as quadratic. If you see these set of order pairs here, notice how they do kind of make a U shape. So it looks like there could be a parabola drawn through the middle of the data that could be used as a predictor of certain events going on. And notice how this one kind of curves the other way. And remember, with quadratics, this would be considered, this would probably have a maximum, and this one over here would probably have what's called a minimum located at that vertex. So we're going to study data that may look quadratic or linear in this section. So with quadratic relations, it may be important to identify the vertex. Remember, if the graph opens up, it is a minimum. If the graph opens down, it is a maximum. So again, don't forget about that graphing utility that we use to find a maximum and a minimum as well. So we may come across using those tools as well, the maximum tool and the minimum tool on the graphing calculator. So let's put this together with an example. So we have a life cycle hypothesis. So let's see what this one is. An individual's income varies with his or her age. The following table shows the median income of males of different age groups within the United States for 2016. For each group, let the class midpoint represent the independent variable, X. And for the class 65 years or older, we're going to assume the class midpoint was like 69.5. So we're going to use that as some data points. So let's see what the first set of directions ask us to do here. So use the graphing utility and draw a scatter plot of the data. And we're also going to use this zoom 9, which actually, how we had trouble fitting the graph to the window. Zoom stat will automatically fit the window to the data. So that's what we're going to be taking advantage of that this time. I didn't see that last time, so we're going to take advantage of that zoom stat feature. Pays to watch some videos. So let's see if we can kind of make this happen here. So to enter data, again, we got to make sure, if we look at y equals, we want to clear that out. Under stat plot, we want to make sure we have something turned on. And you kind of see right over here, it kind of says plot 1's lit up, so I think we're okay there. But if I go ahead, it's the second y equals, you kind of see plot 1 is on. If we need to turn that off, we can do that later. But right now, we can just let that be. From there, if we hit the stat button, remember, if we use the edit button, that's where those lists come from. So we can clear list 2, come over, highlight L1, clear that data as well, come back down. So the X's are the class midpoints. So between 12 and 24, they're using this 19.5 to represent that category, 19.5. And then we have this 29.5. And then we have this 39.5. And we have this 49.5. And we have 59.5. And we have 69.5. All right. So the X's are entered. And then this is getting into what they call the median incomes for these categories. So if you're around 19, or if you're in the ages 15 to 24, your median income would be around 12,396. Remember, your calculator does not have a comma, so don't use a decimal point there for a comma. So for ages 25 to 34, the median income is 38,152. So if you're between 35 and 44, your salary is 51,443. And if you're 45 to 54, don't see much change there. Kind of settled in, didn't it? Kind of peaked out there, around there. And as you got older, all of a sudden we're seeing your income actually dropping 47,001. Try that again. 49,001. And then we have this 31,000. So 65 years and older drops way down. 31,618. All right. So it looks like your salary kind of starts out slow, your income does, and then it kind of peaks out and then it goes back down. So it sounds like it has a maximum value. And when you talk about maximums, there's a darn good chance this is going to be quadratic that opens, and the problem should probably open down if we look at the data. Let's see what happens here when we graph this. So to graph this, what I'm going to do is hit zoom, and number 9 says zoom stat. So I'm going to hit that one, number 9, zoom stat. It sounds like it fits statistics stuff. So, and notice how we do get our data points graphed there. So we should have 1, 2, 3, 4, 5, 6 data points. 1, 2, 3, 4, 5. So notice how it does look kind of parabolic. It opens kind of down. So there's our data. So determine the quadratic function using the quad regression. So we're going to round A, B, and C to 3 decimal places and graph it. So to do this, we're going to go back to statistics. And remember, under statistics, there's a calculate area. So we slide over one to calculate. And number 4 was the linear regression. And right below the linear regression, we're seeing quad regression. So this is supposed to create the function for this problem since it does look quadratic. So I hit enter there, and then we're using L1 and L2. Now that stuff has to change. So hit calculate there. And we're just focusing on the A, the B, and the C. So I'm going to just write over here to start with. So my A is going to be negative 49.778 if we round to 3 decimal places. The B is approximately 4,797.963, since we have to round out that 2 to a 3. And your C is going to be this negative 61,402.645. So the quadratic function would be then f of x equals, we'd have negative 49.778 x squared plus 4,797.963 x minus then 61,402.645. So that would be our actual equation. So we're now going to use this function to determine which determine the age of an individual can expect to earn the most income. So use the function to determine the age which an individual can expect to earn the most income. We're going to use the graphing utility to find the x value of the maximum. And this can also be done using x equals negative b over 2a to find the x value, which can lead us then to finding the actual income. So I'm going to go ahead and try to graph this. So I hit y equals, I have negative 449.778 x squared plus 4797.963 x minus 61402.645. So if we hit graph, let's see if it actually works for us. Got an error. I think I probably hit the negative instead of the minus sign again. I do that all the time. Let's see if we can go to that. Yeah, I did that. So there's a negative there. So see if that makes a difference now if I graph it. Yeah, that looks pretty good. Now, to find the maximum x, I'm going to just use the maximal calculation. So remember above trace, there's this second, if I hit second trace, there's this calculate. And if I go down to 4, I can find a maximum. So if I make a left bound, get a little bit to the left of where I think it is, hit enter. Then if I make a right bound, hit enter again, and it'll take me to the age. And I believe the ages are rounded to the tenths place. So we'll use 48. So 48.2 would be the expected age where your income would be maxing out based on this data. So if I want to determine the peak income, that would be the y value. So the peak income would be, and if we round this to the nearest whole number, this would be like 54,213 if I round that to the nearest dollar. So that would be the peak income based on the graphical data. And that saves me to doing this all by hand since the graph is there. Okay. So let's see if we can piece together another one of these examples here. So I'm going to hit y equals and clear this guy off. So the following data represents the square footage and rents dollars per month for apartments in La Jolla area of San Diego, California. So this is back in 2018. So let's see if we can follow the directions here. So it says draw a scatter plot. And remember, we can use zoom set to kind of make the graph, the window fit the graph. So under stat, we have to edit our list. So we're going to clear off L2, go over and clear off L1. Now, if we put our X's in, this 520, 625, 710, 765, 855, 925, 1040. So that's the square footage. So it should make sense that as the square footage goes up, the rent should go up. So that sounds like That doesn't sound very quadratic. Doesn't sound like a maximum. It sounds like more like a linear at this point. So 1630, 1820. So notice how the square footage is increasing. The price per month is increasing. That sounds very linear. 1975. Good thing we don't have to pay those types of rents. Ours aren't quite that high here in Kentucky. And let's see here. Whoop. $2,000 for a month. Whoa. And then 2,360. And this is back in 2018. Things are a lot higher now too. So, alrighty. So if we hit zoom and choose number 9, notice how it creates our data. And it does look very linear in that. So we did one is to plot linear or quadratic. So I would say, based on what I'm seeing here, this data does not look, it looks more linear. So we could do that. So when I write the function, I'm going to use the linear regression line here. So under stat, if we go to calculate, and number 4 is the linear regression. So we need the A and the B there. So we want to calculate that out. So remember the A is the slope. So we have f of x equals, and again, we want to round this to 3 decimal places. So 1.337, 1.337x, and then the y-intercept is a positive, so it'd be like 936. If we round that through 3 decimal places, so it'll be like 781. Okay, so if I go to y equals, if we'll go and graph this, let's see if this actually looks pretty good. 1.337, and we can make that an x plus then 936.781. So if we hit graph, notice that that does go right through our data. So we really feel like this is a good predictor of things up to a point. Square footage does not go on forever. So, but within reason of things, it'll work out pretty good. So we want to use this function to predict the rent for a 875. We want to use the function to predict the rent for $875 per month. Round the answer to the nearest dollar. So use the function to predict the rent for, I don't think I like that question there. That should be 875 square feet, probably, not $875. All right, so let's see if we can edit that a little bit. So because we're trying to predict the rent, this 875 looks more like a square footage. So predict the rent for 875. This should be like square feet. Now this problem would make sense to us. And round the answer to the nearest dollar. So all we really got to do is substitute the x of 875 into this function. And since it's not too hard, we can probably just use a calculator for this. 1.337 times 875 square feet plus then this 936.781. And this should give us an idea of what the rent should be as a predictor. So if we get out of the graph and put in 1.337 times 875, then if we add the 936.781, hit enter. So we're going to get 2,000. That looks like that fits in line with what we're seeing here. So we're going to round the answer to the nearest dollar. So $2,107 would be that one. Okay. So some of the data will not be quadratic, it may be linear or vice versa. Let's do one more example and see where this takes us. So which the following data represents the birth rate per births per 1,000 people, population for women whose age is A in 2016. So we have, like, for somebody 16 years old, there's 8.8 births for every 1,000 people, 1,000 population. So I'm assuming women there as well. So if somebody's 19 years old, 37.5 births are happening per 1,000. So it's not a huge birth rate there. You kind of see most people are waiting till really in their late 20s and early 30s to have children. And that sounds reasonable. By then, most people kind of are ready to settle down and make some roots. So notice how this kind of mirrors a maximum value here. This kind of looks quadratic just by looking at the data and everything. So let's see if we can make a scatter plot that kind of fits that. So let me see here. We go to stat. We want to edit, and we want to clear those off and put some new data in. So we have a 16, 19, 22. So we're changing by every 3 years, kind of there. It started out 3, then it went up to 5 there. So not perfect data there. There's not this constant change in the X's. So that's why we just call it, it's collecting data. It's not going to be perfect. But does it create a pattern is the question. So I have a 8.8 per 1,000, 37.5 per 1,000. So that's not a whole lot of babies being born. 73.8 per 1,000, 102.1, 102.7. So it looks like around there it starts to peak out. So around age 32 or so, 52.7, then it drops back down, and 11.4. So if we hit zoom and choose number 9, notice how it fits the data for us. And it does it looks very much quadratic there. So if we draw the scatter plot of data, does it represent a linear or a quadratic relation? It looks very much quadratic. So determine the correct function. So we're going to use the quad regression. So if we go to stat, go to the right, go down to quad regression, it'll give us that A, B, and C, which are going to be the values that we will use to create the quadratic function. So yeah, we're going to L1, L2, all that stuff stays the same. So I'm just going to make a note down here. A is negative 0.561 if I round to 3 decimal places. B is going to be 32.5. Looks like 550. If I round that to 3 decimal places. And C is going to be negative 371.675. So if I have that going on, my function is going to now be f of x equals, or actually you could say f of a here, or even better yet, if you want to get real cute with it, you know, we could be using b of a if we wanted to, where b stands for births and A is the age. So I could do like B of A as my function if I want to get cute with it, kind of stay with this notation over here. So I'd have like negative 0.561 x squared plus 32.550x minus then 371.675. So let's go ahead and put that in the calculator and see what that graph looks like. We'll clear that one off. So we have a negative 0.561 x squared plus 32.550 x minus then 371.675. So again, if I hit that zoom and hit number 9 for stat, I'll say, yeah, that looks really good. It goes through the data points really nicely, cuts through the middle of them. And that's what you want. Something that's a best fit do is go through the data. So from here, it says use the model, predict the birth rate of a 35-year-old female. You can change the table set from auto to ask and round your answer to the nearest 10th. So what we're doing here, instead of trying to do this by hand, if we go to table set, so if it's second table set, what I can do is go down here and change the independent variable to ask, hit enter. And now when I go to my table, if it's second table, I can now input my values. And since they said the age of the female is 35, if I put 35 in, it'll put the 35 into the function for me and do the math of 80.35. So that seems to be in line with some of this because we're getting on the other side of 32 and 37 was 52. So somewhere between 102 and 57 seems very reasonable. So if I round that to the nearest 10th place, that'd be 80.4. So the birth rate for a 35-year-old would be an 80.4 would be the birth rate. All righty, so that kind of gives you an idea of how data can be used to help, generate data and, kind of make predictions. But again, these are just predictions. It's not a one size fit all when it comes to data. So there's always something that doesn't fit the data. So just keep that in mind. But in general, this is what you'd be expecting. All righty, we'll stop there.